So this is the third lecture on this topic of enumeration of maps. So last time, we've seen in the first lecture how we could produce functional equations for counting families of planar maps. And in the second lecture in the afternoon, we saw, at least in theory, what we can do to try to solve them. They are of a rather specific form. So this morning, so that's lecture 3. Well, maybe before I start, if you happen to have questions on last week's lecture, that would be one way to start. You have questions? Nope. Okay, so I'm gone. So this morning we'll do two things. So first, I want to show you some computer algebra tools. So in Maple, since I'm using Maple, so that will be the first part. So some Maple tools. And then we'll look at another kind of functional equations that are also helpful to count maps, which are also old and date back to Tutt's early work on the topic, which are composition equations. Okay, so I'll start with the Maple tool. So what we want to do, so I told you that we could write functional equations and that there was a procedure for solving them by taking some resultants between this and that equation. So what were these and that equations? Remember that we had typically some polynomial, in fact, very often a rational function, but it makes no difference, that relates, say, our main series for maps, one of its specializations, so typically M of 1 here, and T and Y, and this was 0, and I should tell you that M of Y was the generating function of planar maps counted by edges, and the outer degree, which was the degree of the outer face. So you remember that I'm not recording here in the notation the size variable t. And so we had a recipe for addressing this type of equation. So this polynomial, say, depends formally here on 4 variables. And so the recipe was we should look at the first derivative of the polynomial and find some series y. So this is some y of t, such that this equation also holds. And then this implied that also the last derivative of this polynomial evaluated at this same point was 0. And of course, we had the original functional equation. And so the idea was that these 3 polynomial equations in 3 unknowns, M of 1, M of y, and y, should hopefully determine all 3 series, provided we had a few initial coefficients. So that's what I want to implement now on 2 examples, general maps and triangulations over polygons. And then, so as we said last time, this yields algebraic equations for, say, M of 1, from which we can compute coefficients, which are often very nice. So I also want to show you some tools, first to guess coefficients, even though here that's a problem we can solve, but these tools can be useful in other contexts. And then once you have the equation, how to prove these nice coefficients. So is this large enough? Can you see? Philippe, bonjour. Is this big enough, or would it be better if it were a bit larger? It's okay? So I remind you that you should speak. I don't want to be the only one who speaks. But now that Philippe is here, I know that you will speak. Okay, so general maps. No, but I can send it to you, or I can put it on my website if I think of it, but I should take notes because I'm brainless. But then I should clean it so that you don't see all the dirty things I'm doing. Okay. So is it still big enough with that? Now I'm asking which. Yes, okay. So that's our equation for maps, which we had written 10 times. M, so this stands for M of y, is equal to 1 plus, this was the isthmus case, so this is M of y. Here you have the divided difference, and with M1, which stands for M of 1. Okay, so now this is written as a formal polynomial. So before I apply the recipe, I want to show you some general tools that you can apply if you have been able to produce a recurrence relation or a functional equation and you have no idea what the answer could be. Okay, so the first thing I'm doing here is something rather shameful. So I have this functional equation. I want to use it to produce the first few coefficients of the series. So this is a series in T, the size variable, recording the number of edges, with polynomial coefficients in Y. So the rather silly thing I'm doing here, and I should be shameful in front of computer algebra people, is that I'm just iterating the functional equation, you see, which I can do thanks to this factor T. So I say the initial term, the initial coefficient is 1, and then if I want to compute up to order n, I plug the series up to order -1, expand things up to order n, and I get the series. So this is what this thing is telling you. Of course, this is a silly way of doing things because each time when I want to get up to n, I'm doing something that I've done up to order n-1. But if you want to get just an idea, that's something lazy that you can do. So here are the first terms of this generating function m of t and y. So you see, for instance, with one edge, you have two maps with outer degree 1 and 2. So one is the loop, which has outer degree 1, and the other is just a bridge with outer degree 2. Okay? And this goes on. So if I want to ignore the outer degree, I replace this y variable by 1 and just get, say, the first 10 coefficients, which are the number of planar maps with n edges. So these are very general tools. So I would like to know if there's a chance that these coefficients are nice. And one very basic notion of being nice is having small prime factors. So here's again my sequence, ordered backwards. So I look at the prime factors of these numbers, and they don't seem to be very big. So maybe there's something that's happening here. If I do the same for the whole series, so now I look at the bivariate series, so maybe the coefficients are still nice. That is, maybe there's a nice formula for the number of maps with n edges and outer degree k. So here are the coefficients, whatever they are, and I want to factor them, and I claim it's not so nice. So you see here, I get something that's a bit suspicious, rather big. Here it's even bigger, or there's a terrible one. Okay, so maybe there's no very simple formula in that case. Okay, so now that's a slightly better way of computing these coefficients. So mco is the coefficient of t to the n in my series. And here I'm just implementing the recurrence relation which underlies my functional equation. It is either I glue two maps and add a bridge, or I add an edge that creates a new face. And I realized that if I want this to work, I should do it. There we are. Okay, so here so this goes a bit faster, of course, well, much faster. So my new series M ser now, I'm building the series coefficient by coefficient. Okay, so now here comes some more, again, general tools that you can use for any problem, provided you've been able to compute the 10, 20, 50, 100 first coefficients of your series. And these are based on a package called GFun for generating functions, which was developed already more than 20 years ago for the first version by, at first, Bruno Salvi and Paul Zimmermann, and that you can find on Bruno Salvi's webpage. So it's still updated regularly, so it works with recent versions of Maple. Okay, so one of the first things that GFun can do for you, you feed it with your first coefficients, and it tries to guess if this generating function could belong to one of the nice classes I defined last time. So you may remember I had this hierarchy of formal power series, and the simplest ones were the rational series, then came the algebraic ones, then the definite ones, which are those that satisfy linear differential equation with polynomial coefficients, and then I had this nasty class of differentially algebraic series, which are not implemented in GFun. So here I compute the first, I said 30 and I expanded up to order 21. This is a shame, but maybe this would be less stupid. It doesn't want, okay. I want it to be a series. So the first thing I'm trying here to follow my hierarchy of series is to try to find a rational series that would match these terms up to order 20. And so this is not GFun, this is in Maple, so that's constructing a pade approximant of the series. So that's convert my series into a rational polynomial. And I get something that's not especially encouraging. So I could go on with more than 20 terms. But then, so the next command is a GFun1, series to algebraic equation. It takes a series, and it tries to find an algebraic equation that seems to match with these coefficients. So that's the one. And you see the result here. The GFun has guessed that my series M, as a series in T, so that's the size variable, seems to satisfy something quadratic, so which is very encouraging. Once you have guessed something like that, you feel happier. Okay, so I give a name to this equation, and if I want to get an idea of the coefficients, which I recall seemed to have small prime factors, I construct the corresponding or a corresponding differential equation. So I told you that every algebraic series is definite. So it must satisfy at least one differential equation. And so here, in fact, I don't construct it. I guess a differential equation. So indeed, there seems to be one of order 2, which I call DEM, differential equation for M. And then if you think a bit of what it means for a series to satisfy a linear differential equation with polynomial coefficients, it means that the corresponding coefficients of the series satisfy a linear recurrence relation with polynomial coefficients in n. And so, yeah? Yeah. Yeah, I'm not applying my recipe yet. Yeah? I could construct, yeah. Yes, it does, yeah. Yeah, yeah. Well, in some cases, I suspect that it won't. I mean, it doesn't always guess a minimal differential equation in terms of order. And so here I'm just doing guessing. So I've guessed an algebraic equation, then a differential equation, ignoring my first algebraic result. And here I'm guessing from the series a recurrence relation, which happens to be first order. So that's this one. Okay, so M, the number of maps of size n plus 1, should be related to the number of maps of size n by this equation. And of course, this is very attractive. So we have n plus 3 times the number of maps of size n plus 1 is 6 times 2n plus 1. And from this plus the initial condition, you would get the formula that we proved last time, namely okay? So these are very general tools. You have your 20, 30, 50 first terms. You can try to guess algebraic equations, linear differential equations, or equivalently recurrence relations between the coefficients. This tells you something. So here on this example, this recurrence relation can be it's first order, so you can solve it directly to get this hypergeometric form. But there's also some procedures now in Maple that allow you to find, for instance, hypergeometric solutions of linear recurrence relations. So imagine you had found something of order 2, and you still hope that maybe your numbers are nice. And by nice, I mean hypergeometric. So what it means, a sequence is hypergeometric if the ratio of two consecutive terms is a rational function in n. So obviously, this is the case here. So you also have in Maple a useful command which computes hypergeometric solutions of any linear recurrence relation. So now this is a bit ridiculous because I'm applying it to a first order equation whose solutions is obviously hypergeometric, but well, so that's hypergeom solves, and it gives me the solution in terms of gamma functions, whereas I've written it here in terms of factorials. Okay, so that was the guessing part, which you can apply to other problems. And now I'll get to the solution rather than the guessing. So this next section here, so that's really applying the recipe that you have on the left. So here's my equation, which is rational in M, T, Y, and M1. Okay? So the first thing I'm writing here is the equation that the big Y, the series big Y, should satisfy. So I'm differentiating my equation with respect to the first variable. And this we had written last time. So that's the equation that Y should satisfy. Okay, and as we had argued, there's a unique, because of this factor T, there's a unique power series in T that solves this. And then I'm saying that the last derivative should also cancel. So now I have here my three equations relating what is here a small y, but is really my series big Y, the value of m at this point, and the unknown series m1 in which I'm interested. And then what I did here is just taking resultants. So I have three equations. I can get rid of one of the unknowns, say m of y, in two different ways by taking resultants. So I get a first equation between two unknown series, m1 and y, a second equation of the same type, whatever they are, and I get rid of the y and get a polynomial equation for m1, the generating function of maps counted by edges. So you see that there are several factors. So I told you about this possibility last time. But since I know that, so for instance, if we look at this one, could M1 satisfy this equation? Well, this, whatever M1 is, this is a power series with a non-zero constant term, 4. So there's no way that this could be 0. This will happen to be the correct one. And this has constant term 1, so certainly this factor doesn't vanish. So here we found the algebraic equation for M1, which is, of course, the one that Maple or Giffen had guessed formally. Yeah? Sorry? No, not necessarily, but if, I mean, you can always, given that you can compute the first coefficient of M1, you can always end up, if you compute them far enough, decide which one actually cancels. Are there more questions here? Okay, so we have a quadratic, we solve it. We take the solution that is a power series in T. There's only one of the two, or otherwise the one that coincides far enough with M. And so this is the generating function of planar maps, which I can expand. And this is the formula that I typed here. So in this case, it's so explicit that proving the nice form is just an expansion. This is just a binomial formula. But I'll show later some tools that allow you to go from the equation, from the algebraic equation, to the formula. So this was the general recipe applying to equations of any degree, and with, in fact, an arbitrary number of auxiliary series that depend only on T. But I had told you that there was this so-called quadratic method, which was essentially doing the same thing, but is described in slightly different terms, and which you can summarize by saying that the discriminant of the discriminant vanishes. And what I mean by that is that you take your polynomial, you first compute the discriminant with respect to this variable. This is a polynomial in these three things. And in this polynomial, you take the discriminant with respect to y. And then this should be an equation between your unknown series M of 1 and T. So this is really, this is really nice. That's two lines of Maple. Discriminant of the discriminant is 0, and this is your equation. So that's what I'm doing here. Starting again from my functional equation. Yeah. Okay, so I'm taking the first discriminant with respect to M. I get some delta. And now the quadratic method tells you that this delta as a polynomial in Y has a multiple root, Hence, its discriminant should be 0. And here you get a polynomial equation again for M1. So we have fewer factors. There's still this factor that you don't want, squared. But the main equation here is no longer squared. And the other factor you don't have. And in fact, in all these method recipe, and especially when you have several of these additional series like M of 1, I mean, there's still some mysteries about the factors that occur and the multiplicities of the factors that occur. In a sense, in many cases, I have this feeling that I'm computing things that are too big because they factor, they have multiple factors. And I think in some cases, the way I'm doing things prevents me from getting to the result, because Maple, even if the final result, the final equation happens to be small and nice, Maple is computing something very big and sometimes cannot compute this very big thing, whereas in many cases, you have huge computations and you end up with something that nicely factors, and your final equation is one of the small factors. So I think that there's still some algebra and computer algebra to do to improve this. And because I have precise examples in mind, we'll see one in this course. So for instance, I can prove using this that planar maps, or say the Potts model on planar maps, that is 3 colorings on planar maps, where you record the number of edges that are monochromatic. So that's edges in which both endpoints have the same color. So this is algebraic. So this is given by the theory. But I can only obtain effectively an algebraic equation if I restrict my attention to proper colorings, so no monochromatic edge. And there the equation is ridiculously small. So if I could, so now I'm trying to catch the attention of the computer algebra people or of the algebra people among you. So if I could do differently these calculations, I may find for the general problem an equation that's also small, but that at the moment I'm just unable to compute, which is a bit disappointing. Okay, so this being said, here's again our equation. So that's another command of GFEN which you haven't seen so far. When you have an algebraic equation, it has a number of solutions, and you can, so here too, you can compute their expansions around 0, for instance. So first I remove this option true just to show you the 2 roots of this algebraic equation. So one starts with the term 1 over t squared. Certainly it's not my solution. And here I've added this option true, which selects the solutions that are finite at t equals 0, so the non-divergent solutions. Okay, so that was the shortcut, somehow, this quadratic method as a shortcut of the general recipe. So now we have the algebraic equation. Here it is. So now we can convert, if we want the coefficients, we can convert it into a differential equation. And this is no longer guessing. This is really computing. So this is rigorous. Okay? So you know if M1 satisfies this, that it also satisfies this differential equation. And from this, you compute a corresponding recurrence relation, which is, of course, the one we had guessed. Okay. Yeah? Yeah, so here if you start from something of degree d, an algebraic equation of degree d, it will return a differential equation of order d minus 1, I think. Yeah. Yes, exactly. Yeah. Okay, and then you have obtained this recurrence relation, so you have proved in one more way this nice formula. Here's another, yeah? Yes, I think that some coefficients could vanish, some coefficients a smaller degree. I have to think of this. So saying that it is algebraic of degree d says that you have a vector space of dimension d plus 1 that contains all powers of m. And so certainly this vector space contains all, it's also a field and it contains all derivatives of m. Now, could you have something of smaller order in the differential equation? I don't see that it's not possible, but I'd have to think of it. Okay, now one more classical tool to obtain closed form expressions once you have guessed or established an algebraic equation is this Lagrange inversion formula. So I should tell you what this is. It's a very classical and useful tool when you want to compute numbers. So say you have two formal power series phi and psi, which are formal power series, explicit, and you are interested in some series A, which is a series in some variable t, which is given by a functional equation of the form A is t times phi of A. So in general, this doesn't suffice. You need also to say that A has no constant term. And we'll see here examples of this type. And you are interested in the coefficient of n in psi of A. Then, maybe I should write below, this is 1 over n times the coefficient of t to the n minus 1 in phi of t to the n times the derivative of psi. So we'll see how to apply this. Now the question is, can we apply this to our problem? That is, what we have at the moment is some polynomial equation relating our series, which is m of t, and then t. So that's our solution. We have proved that. Could you, by any chance, write that there is, so that's question mark, that there exists some phi and psi such that we can write, we can introduce a series A, some auxiliary series A, such that so can we apply this? That is, can we write T as A over phi and M as psi of A? So if we add to this the condition that phi and psi are rational, then, so you really want to write that T is A over phi of A. So now you have your curve here, P, and you're looking at, for two rational functions, say 1 over phi and psi, such that T and M, which are related by this polynomial equation, can be written rationally. That is, in different terms, you're looking for rational parametrization of your curve. So I am essentially ignorant in algebraic geometry, but this is a classical question. And the answer is that such a parametrization exists if and only if the curve you have obtained here has genus 0. I don't know how the genus is defined, but Maple knows how to compute it. And if the genus is 0, then Maple can also compute a rational parametrization. And then you can apply this Lagrange inversion formula to compute your coefficients. OK, so here's my curve, which relates the variable t to the generating function of planar maps M1. So that's another package, algebraic curves. And I ask what the genus is, and it tells me that the genus of the curve is 0. So there must be some rational parametrization. And I'll be in a good state to apply this Lagrange inversion formula. So here's here's one parametrization. So Maple is able to compute one. But often it's not given in a very nice form. And so very often, so I'm giving you all my not so elegant secrets, so I have to fiddle a bit with the parametrization that's given to find one that has nice coefficients. And I never found nor really looked for a very good way of doing that. So the one thing that you can do, so if you have one rational parametrization, so this, sorry, I should explain what it means. So I'm giving the curve, the two variables, and some additional name. So S will be my A, so I should call it here probably S. So will be the auxiliary series that I have to introduce, and that parameterizes my curve.
So the expressions here are expressions for t and
Exactly, thank you. So what this says, I'm forgetting important things here. So what this says, if you have this symbol or arbitrary thing here, S, then if you write T of this form and M1 of this form, then the algebraic equation that we had at the top holds. Yeah? Okay, so that's a good point. So S is something of order 2, as you would expect. So there are several solutions. There are several series S solutions to T is equal to this rational function. For one of them, and at some point we'll have to decide one, M1 can be written like that, not for the two. So at some point we'll have to decide which S, and you see here, typically we want to have something that has constant term 0. Yeah, so that's one of the things I would like to reach at the end, because then this S will typically count trees in those cases, and this opens the way, or at least the hope, to find more combinatorial derivations of the results in terms of trees, and this is what was done in the decades that followed the TUT results. So that's the rather ugly part. So if you have a rational function that parameterizes your curve, any homographic transformation is also a parameterization. So here, so did I execute this? So here I try to fiddle with this. So I want to find some A, B, C, D that make my parameterization nicer. And so in my papers, I always hide these ugly parts, but today I'm showing this to you. So maybe I don't want here any denominator. So this forces, so I have 53 SA minus 2SC. So I want 53A to be 2C. That's not what I'm doing here. So I simplified first the numerator. And then I said, horrible. Okay, so I have to do it. It has changed. That's horrible. Okay. So now you'll see it in real time. So what do I want to do? So let's ignore this. And I was saying that maybe I want this denominator to be simple, to have no S. So 53A should be 2C. So let's go for that. A is 2 times C over 53. Because this will be my A, or S, this will be my basic functional equation, and it should rather be simple. So for instance, if I can get something like, so here I'm heading to a quadratic, so S times S minus some A, then I will have S will be given by T over, so say A minus S. And this will be a nice phi to compute its powers and extract coefficients and whatnot. That's just one choice. I mean, you can. OK, so here I have, with this choice of A, I have killed the denominators. Now I would like to have one coefficient here that would be just S with no constant term. So what will I do? Maybe B should be 53 times D. So you see, it's not stable, this parameterization thing. And in fact, when I was preparing this, I tried to put. You're telling me this.
Oh, is that it?
Yeah. Yeah, I would like to this to be 0. Okay. So yeah, I was just telling you of one curiosity. I mean, if sometimes when I replace this S, which should just be a symbol by some A because it fits with my notation, I get a different parameterization. So And this, I promise, I executed yesterday in the train. Okay, that's life. So now I've reached this thing, and now what do I want? That my, say, this could be S minus 1 typically, so say should be 53 times d over 4. Ah, what a nice parametrization. So what is this telling us? So you'll read it for me. So what did I find here? That if T is of what form? So it's S1 minus S over 3. So S should be 3T over 1 minus S. So that's my T phi of T, phi of S. For those of you who are familiar with trees, this S should count certain trees. And then I expect M1 to be this, we are not there yet. Okay. So that's what I was saying. So we have here a nice parametrization, but for which of the roots S of the equation T equal S minus 1 over 3 is M1 equal to that? Not for both. So I'm taking the equation T is equal to that.
Sorry,
yeah.
Can you repeat which roots? Or the first equation?
Yeah. So this equation here, T equals that, has two roots in S. So there are two series S that cancel this. M1 cannot be equal to that for both series. So I need to know for which one, for which value of S, M1 is equal to that. So that's why here I'm computing the expansion of the two series. And then for each of them, I plug this into the this expression, and I see that only for the first one I get the generating function of maps here. So that's a little subtlety. So really I want S to be something like that. So 1 minus 3 times T. So hence my final substitution here. So here I get the same equation, but now a different expression of M1. Okay? So this equation, again, had two roots, one that has no constant term in T and the other that starts with 1. And for the one that has no constant term, I get that M1 should be 3 minus 4S over 3 times 1 minus S squared. Okay, so I don't think I'm going to do this calculation for you, but once you have your rational parametrization, you can apply this, and that's another way, rather lengthy here since we had other possibilities, but in some cases where you won't get any nice hypergeometric formula, then this is one way of obtaining coefficients. Yes. So I've reached, where am I? I've reached one parametrization here, which looked nice, but I still need, so I want to apply this to a series S having no constant term. So now I have two roots of the equation T equals that. one has no constant term, and the other has constant term 1. So am I in the correct situation where I could apply this? And this should be the expression of M1. So I compute the expansion around 0 of the two solutions of t equals that. So the one that starts with 1, the one that has no constant term. I plug them in this rational function, and I realize that it is the first one, that is the one that starts with 1, that is the correct one. So that's why I write that my former S was some 1 minus t or S. I get here the same equation because it was invariant by this transformation, but here a different expression of M1. Okay, so these are little tricks. So we have applied them to a rather ridiculous quadratic example where we could do everything explicitly and upon expanding a binomial. So I want to show you the same thing for another problem that we had looked at last time. Are there questions on this example? Yeah?
The curve is positive t.
No. But so that's another mystery. Well, it's no longer a mystery, but it used to be one, that all these equations that you get for planar maps, for many, many families of planar maps, had genus 0 and a rational parametrization. And this is, so a rational parametrization of this type, or, of when you write that S is t times phi of S, so that's t times the sum of, say, some coefficients phi I S to the I. And when you write this, you are just counting certain plane trees with weights phi I on nodes that have I children, okay? So the existence, a more combinatorial way to phrase the existence of rational parametrizations, that is of all these curves having genus 0, is to say that there are trees hiding somewhere in those map problems. And this was somehow one of the observations, in addition to having nice numbers, but these nice numbers come also from the existence of trees that led people to look for bijection between maps and trees, and that led to all these nice results in the 90s and since then. But of course, in some cases, for some problems, we find curves that do not have genus 0. Even for some families of planar maps, for instance, if you look at triangulations in which you forbid vertices to have a small degree, for instance, you don't want vertices of degree 1 or vertices of degree 2. So this is normally a hard problem because in general, forcing conditions on face degrees and vertex degrees, that's hard. So triangulation is a condition on face degrees, and having vertices of high degrees a condition on vertex degrees. So that's a difficult combination, but quite a few years ago now, Olivier Bernardi was able to write functional equations of that type, or of the type that we wrote last time for these problems, and there you get some families that have no underlying trees. So I guess if you get a curve of genus 0, you can decide so that you have elliptic functions around, and you can try to parameterize this in terms of Weierstrass functions. Okay, so now the next example where I'm going to repeat the same things is the case of triangulations of a polygon. So remember, we wanted one, two, three, and okay. I'm not sure it's correct, but we wanted the outer face to be simple. That is, no cut vertex in the outer face. So we had also written one of these equations with one catalytic variable, where P was the main generating function, and now P1 That's the coefficient of y in the series. So the series that counts maps with outer degree 1, that is triangulations of a one gun. So I'm doing the same thing. I'm expanding the series. I realize that there's small factors. So here I apply directly this quadratic method, saying you have your equation, the discriminant of the discriminant vanishes, and I find this rather charming. This is 2 lines of maple. Here's the first discriminant. No, sorry, this is the equation. I take discriminant with respect to P of y. So that's the first one. Then with respect to y. And here I get just directly the equation. You see there's no additional factor. So this time we have a cubic. Okay? So for general maps, we had something quadratic, which we could solve explicitly. And we could compute coefficients just by expanding the solution. But here we are not going to solve a cubic. So what am I doing here? So this is probably not needed. There is here some periodicity, because in a triangulation of a one gun, here's one. So we had counted them by edges. But then you can realize that n has to be 2 mod 3. So you have periodic series, which you can actually see here. So your series starts with t squared, which counts this triangulation of the one gun. And then you have powers t5, t8, and so on, which is not so pleasant. So I'm replacing the edge variable t by a vertex variable w, like vertices or vertices. And so here's the corresponding. So here I've written the corresponding cubic for triangulations counted by the number of vertices. Okay. So here, so from the cubic algebraic equation, I compute the differential equation. Here it is, order 2. And then a recurrence relation, which again happens to be first order here. Okay, a bit more complicated than what I had before. So P1 of n plus, sorry, of second order, that's an important point. P1 of n plus 2 is some simple rational function times P1 of n. Okay. And so you can solve this by iterating, and that's the coefficients you get, which were indeed the coefficients I found in my series. So here I should point out that if you ask Maple to look for hypergeometric solutions of that, it will tell you that there's no such solution because the series, the sequences that are actually hypergeometric are P1 of 2n and P1 of 2n plus 1. So you're missing them even though there's a nice closed form expression here. So that's what I did here. So of course you're safe because you can solve this even though Maple can't. But so you get nice formulae. Well, maybe an alternative is using this Lagrange inversion formula. So who knows whether this will be the same. So here I'm trying again to fiddle with the parametrization to get something decent. So here I get that if I write W, the vertex variable, as this cubic, then for one of the 3 series S that solve this equation, the generating function P1 is equal to this polynomial. so now, so I should so these are the expansions at 0 of the 3 solutions of W equals that. So there's one with constant term a quarter, one with constant term a half, and one with no constant term. And which one, the second one, is the correct one? That is, if I replace S by the second series here, I get the generating function of triangulations of polygons. So this leads me as before.
The third one still seems to be.
Yeah, but with the minus, that doesn't count anything. So I replace S by a half minus A. Now I'm back to my A notation. And so here is what you get. If W is this polynomial, then P1 is that one. Okay? So you found your parametrization, and that's another way of getting coefficients. And in fact, in this case, so I'm not going to give all details, but you can, so that was to compute coefficients of P1. But you may remember that in this problem, it seems that maybe the whole series, that is the series with the y variable, had also nice coefficients. So you may wonder if there's a nice formula for the number of triangulations of a k-gon with n vertices. And this happens to be the case, and you can do the same thing. So then we had worked with P1, but then you can try to parameterize the whole series, P of t and y. So for this, I return to my quadratic. So again, I write now the equation with vertices rather than edges. So this was my parameterization for P1. I plug it in the main factorial equation. So now I have a different curve. So A is the series that satisfies a nice equation, and there's still y. So that's an equation for the whole series P in terms of y, the variable that records the outer degree, and some series, nice series, tree-like series A. And so now I look at this as a curve in y and p, and I'd like to parameterize that in order to be able to extract coefficients. And this one happens also to have degree 0 and the parameterization, so I'm doing whatever I can here. And is that nice? Okay, so here, that's one possible parameterization. There was a nicer one that I have in my notes. No, that's the one, in fact. Okay, so here you get something to which you can apply the Lagrange inversion formula. So now you have your two variables. You first extract the coefficient of y to the k to count triangulations of a k-gon, and then of w to the n to know how many of them have n vertices. And you get a nice expression. I'm going to So I'm going to write this formula because somehow, well, we should use it someday. So by applying twice this Lagrange inversion formula, you obtain that the number of triangulations of a k-gon with n plus 1 inner vertices. So these inner vertices are those that do not lie on the boundary, on the outer face. So here, for instance, I just have one inner vertex. So it's so T of n plus 1 vertices and a boundary of size k. So that's 2k 8 to the n 2kk, and then you have something 3n over 2 plus k over n plus 1 divided by n plus 2k 3n plus 2k. Okay, so this now confirms what we had seen when we had produced coefficients and observed that they had small prime factors. So here's a closed form expression that confirms this. Here, when I'm writing, maybe I should explain this, some ak, where a is not necessarily an integer. So that's a minus 1. A minus k plus 1 over k factorial. So there's other ways of writing this with double factorials. Maybe you've seen that instead. And in fact, there's a much more general formula, much more recent as well, for triangulations, where not only you have this outer face, but you have several holes, but that's not directly what we are doing here. Okay, so if I summarize this part, you have tools for guessing results and for guessing if they belong to the first 3 steps of this hierarchy of series: rational, algebraic, definite. You have tools, so you have the recipe that gives you algebraic equations. You have 2 kinds of tools for getting coefficients from that. Either you compute a corresponding recurrence relation on the numbers and look for its hypergeometric solutions, or you compute, if there is one, a rational parametrization with which you can apply the Lagrange inversion formula. Okay, and I guess this ends my Maple session. Are there some questions on this part? So this is going a bit fast, but you should know that these tools exist and that they are waiting for you to use them. Yes. So I don't know of anything that would do directly the bivariate case. That is, you could think that you start from a system of differential equations, one in t, one in y, and looks for doubly hypergeometric solutions. But I don't know that there exists something like that. Okay, so I'm going to switch this off. I was told that it would wake up. Okay, so video off and screen. Ah, no. Okay, so now I'm moving to the second part of this morning's lecture, which deals with those what we sometimes call composition or substitution equation for planar maps or for maps. So many of them were written by Todd himself in the 60s, a bit later. And so what they usually do is that they relate the generating functions of two families of planar maps. And typically, one has higher connectivity than the other. So maybe we'll take a first example, which is the case of non-separable maps, always planar. So I should first define what I mean here. We say that a map is separable if erasing one vertex, so if there exists one vertex such that erasing it disconnects the map. So here's one example. So typically what it means is that you have a cut vertex. So this is a cut vertex. If I erase it, I get 3 pieces. So this map is separable. I keep the edges. I erase just this little dot. Sorry? I don't get a map. I just get a picture. Picture. Okay, so yeah. So with this definition, this is not separable, and this is not separable either. If I delete this, I get that. Okay. So the two with this definition, so sometimes you will see some different conventions with this definition. The two one-edge maps are non-separable. Okay, so now what we've studied and solved was counting all planar maps M by edges. And now we wonder about the generating function of non-separable planar maps again by edges. So this one we've seen satisfies a quadratic. What about this one? So there's at least two ways of doing that. Either, I told you last week that Tutt's recursive approach was very robust, and in fact, we could try to to delete the root edge in a non-separable planar maps and look at what's left, which may be separable, but has a rather simple structure. And we could write, for this series, a polynomial equation upon adding a catalytic variable y, recording the outer degree, as we did last time. Yep?
When you use this method, then you remove one.
Sorry?
You will say that you take one map.
Yeah.
Not separable, you remove one vertex.
One edge, the root edge, yeah.
Okay.
Yeah.
And then something could be.
Yeah, so what could happen, so if we apply this TUTS method, so certainly this is separable except in that case. So we won't have this isthmus case. But in the other case, where I had something like that, if I take out this edge, what I can find is this kind of I can find something like that with cut vertices here. Okay, so then, but then each of these pieces is non-separable, and then you can describe really in terms of generating functions what happens here. So TUTS approach works on this, but I want to show another TUTS approach, which involves these substitution equations. Okay, so the idea is the following. So you start from a map, M, a general map, so possibly it has cut vertices, and you do the following thing. So for every, so what I call a cut vertex, so that's a point, a vertex that disconnects the map when you erase it. So when you take a cut vertex, when you take it out, so you get several components, and one of them, now I'm having suddenly doubts, how should I phrase it? Say one of them contains the root edge. So at every cut vertex, you delete the components that contain the root edge. So maybe I should take one example. Sorry? So we'll do an example. So maybe already the I have something big. And, okay, so here's my map. I should make it more complicated. Okay. So, and there are several cut vertices. So where are they? So certainly the root vertex was a cut vertex. I have one here, one there. And that's probably it. Sorry? Oh, yes, you're right. Well, there won't be much left. So here, I drop, so say if I take this vertex and I remove it, so there's just this component. So I would drop this component and that one. And the other one is the one that contains the roots. And I do this for every cut vertex. So at the end, so this is the root edge. Maybe I should write it.
Do not contain the root edge.
Oh, detail. Thank you. That's much better. So at the end, what I get here is just this little polygon. So in this little piece that's left, that's sometimes called the non-separable core of the map, I do not have any more cut vertices since I have dropped all parts that were somehow dangling from cut vertices. And so this is non-separable. So this belongs to the family N of non-separable maps. Yeah. Yeah. No. That's, of course, a good question. What could I say? So if... yeah, so anything... So I do these deletions in parallel, and... yeah, well, I don't know how to say that, but indeed I do not create any new cut vertex. So, sorry? Sorry, can you read? Yeah. Yes, yeah, yeah. So somehow these parts will be dropped several times because when I cut here, when I look at this vertex, so this whole chunk is dropped, but inside this chunk, this would be dropped as well. So, yeah?
Why can you not create?
That would be cut point. I should really answer this question. Well, they would have been cut points already in the beginning. I mean, being a cut point is saying that, so say there's one part that contains the root edge. So to go from this edge to the other point, I have to go through this vertex. And so if this was not the case in the big map, I would have had some path from one part to the other. But then, okay, so this was not a cut vertex. And well, maybe one other way of describing this core is saying that I always want two paths go. Sorry? Yeah. Yeah, yeah, that's the same idea, yeah. 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 Yeah, so there's an underlying tree structure indeed that describes how these components are glued to one another. Yeah. Any spanning tree and then? And? Okay, so maybe yeah? Touches the? It depends what you call a component. So for instance, this one I have deleted at some point, but it was not touching the core, but it was belonging to a bigger component. Yeah. No, you can't, but that's why that's another way of saying what I'm trying to say, but not very clear. So, okay, so excuse me for that, I'll get back, I think of it later and get back to it. So now you have obtained, supposedly, I claim that you have obtained a non-separable map, and you want to know in how many ways you can go backwards. That is, what is the generating function of maps from M that give the same non-separable core? And the thing you have to do when you start from N, so from now a non-separable map that I will take slightly more complicated than the previous one. To get a map M that projects on this N, the only thing you have to do is to add in every corner of your non-separable map a little map, arbitrary map. And then, where should this one be here? There's one in this corner too.
On the root edge to be in the...
Yeah, so this was my root edge here. Okay, so this construction, which I realize I'm not describing in a very satisfactory way, tells you that an arbitrary planar map is a non-separable planar map in the corners of which you've glued a smaller map. Now we're going to translate this into a composition or substitution equation So if a map, the non-separable map, has n edges, then it has 2n corners. And what this construction tells you is that a map, counted by edges, is just, so we had the atomic map, say, well, let's put it that way, is just a non-separable map. So you have the size variable t, and then for every edge, you need to plug in 2 maps. So you get here m of t squared. So in other terms, this is 1 plus the sum over all edge numbers, t to the n, the number of non-separable maps of size n times m of t to the 2n, if you want it written down in details. Okay? So in short, m is 1 plus n of t m squared. And that's your first composition equation. Oui? Yeah, you could. So here I have said that it's not, but you could decide that it is, and then you would not have this term. It makes no difference. Both equations are valid. Depends on your convention for indeed this atomic map. Okay. And now what does this imply for the series n? Sorry, you should remember that we know what m is. It's a nice quadratic series. So now we had found, say, some polynomial equation between t and m. So saying that m is a quadratic series. We also have, say, m is equal to 1 plus n of some series that I denote by t, where t is t times n squared. So now I have 3 equations that relate certainly t, m, n of t, and t, 3 polynomial equations. And so if I eliminate t and m, I'll get a polynomial equation that relates the series of non-separable maps evaluated at some t and t. Okay? 3 equations 4 variables. I eliminate 2 of them, and I get this equation. But now T is some big series, and so I could invert this if I wanted to. And so this implies that this holds for some variable T. Okay, so by combining this substitution equation with the polynomial equation for M, we get a polynomial equation for N. I can write it down, but maybe it's not so interesting. Yeah? Yeah, so here I had 3 polynomial equations that relate 4 quantities. That relate polynomially those 4 quantities. So I eliminate 2 of them, these 2, and I definitely get a polynomial that relates n of t to t. But what I claim is that in this equation, I can replace the big T that was a series in T by a small one. And if you want to do it formally, you should say that you invert. So this is, so if you want to do formally, you would write that so that it is what? So essentially, I want to write, so T of S of T is equal to T. So that is, I want to introduce the composition inverse, and if I replace in this equation little t by S of T, I'll get that. Okay? Yeah, but otherwise, I mean, you could do it as well. Essentially, the idea is that this T is not a constant, it's something. So, and so what do you get? So I didn't write here the equation. Okay, so you get a cubic. So you get a cubic equation for the series of non-separable maps. And by applying the tools I've shown you, for instance, converting it to a differential equation and then to a recurrence equation for the coefficients, you find that there are again nice coefficients. So you find that there are 2 n plus 1, n plus 1, 3n, n, non-separable maps with n plus 1 edges. So another very nice formula with a strong smell of trees, here ternary trees, and that was explained combinatorially years later, in fact. So that was our first substitution equation. And then I want to present you a few more that deal with triangulations of higher and higher connectivity. So far, what we've called a triangulation was, or even a near triangulation, was any map in which all finite faces had degree 3. And so this included rather strange beasts that maybe you don't want to include, having loops and multiple edges. Yeah? Yeah, certainly. Yeah. So this afternoon we'll play a bit with non-planar maps, but that will be our only incursion in the non-planar world. They are planar. They are planar. Everything that I'm doing here is planar. Okay, so the second example is say two connected, or in fact non-separable triangulations. So two connected, I mean the same thing as non-separable. So here, so far, we've called something like that. This was a triangulation for us. All faces, including here the outer face, have degree 2. But certainly, it is separable. And in fact, there's a very simple lemma that tells you that a triangulation is separable if and only if it contains a loop. So in the case of triangulations, forbidding separability is like forbidding loops. Okay, so again, there's what we have, which is the generating function P1 for triangulations of a one gun. Which was cubic. And there's what we would like to have, that is triangulations without loops. So certainly not triangulations of a one gun, since a one gun is a loop. Okay, so what do we say here? Well, we take one such triangulation of a one gun, so something counted by P1. So this is the outer face, and inside I have something. And so this something must be cubic, must be a face of degree 3, so this counts for 1. And then I can have two different things. Either I have, again, two loops, that is two triangulations of a one gun, or I have just one map here whose root face is simple. And yeah, so these are the two possible configurations inside my loop. So this was P1. So here, so this tells me that I have a loop and then two of these triangulations of a polygon. And then that's the interesting case, where this piece has outer degree 2, a simple outer face, not like here. And what I do here So how should I call this piece? I call it T. So what I do is that in T, if I look, so T may contain some more loops, of course. And I want to delete them in the same way I deleted cut vertices in the previous example. So if I look at a loop, and more precisely at maximal loops, those that are not contained in another loop. So it looks like this. In T, yes, thank you. So I have this loop. There's something inside. And then here I have a face. I must complete this into a face of degree 2. And so I have something like that with a double edge. Because the other possibility would be that I have my loop, something inside, and then something like that with another loop. So here I would also make a triangular face. So this is my loop L. But then this loop here would not be maximal. There's a bigger loop surrounding it. In this case, L is not maximal. This is. So I repeat, every maximal loop in this smaller triangulation here of a diagon is surrounded by a double edge. Yep. Sorry? No, there could be further things here. There may be several double edges in my T. So what I do here is that I'm going to lose information again. So I had this double edge and inside a maximal loop with things inside. So I convert this into a single edge. So the nice point is that in this way, I certainly keep finite faces of degree 3. I mean, whatever you had around here is now around this edge. And I've deleted all loops. So what I get is a loopless triangulation. Or triangulation of a diagon. Okay, so now I repeat, I started from any triangulation of a one-gon. There was this case. And then what I got here was, well, there's the loop. And then, which symbol am I going to use? Say N2. I've obtained a triangulation, a non-separable triangulation of a diagon. But then there will be something here because I've lost information. So, yeah?
When the first case,
Because I want the degree of this face to be 3.
okay.
So there's 2 possible configurations. So in other words, if I erase the root edge, I get a map of outer degree 2. First case, this outer face is not simple, which means that I have 2 loops attached at the root vertex. And second case, the outer face is simple. So that's this diagon case. Okay, so now the question is, how can I go backwards? I start from this loopless triangulation of a diagon. And I want somehow to inflate every edge, possibly, into something like that. And so, as Philippe is saying, well, I have contracted many things. So I could have several of these, how should I call it, of these eyes that have become a single edge here, provided so here, if I had a loop, and maybe one here, and maybe one here. So I had a maximal loop here, so I have contracted these two edges. I had a maximal loop here, so I have contracted this thing. And so you have these kinds of watermelons. And then in each face of the watermelon, you had a loop, which has vanished. And all this big thing has been contracted into an edge. So to go backwards, well, every edge has to become a watermelon with loops. So an edge, which is counted by T in the series of loopless triangulations, must become, well, a series. So say, here I have K loops. So K could be 0. I could have just one edge. And then I have K plus 1 edges here. And I have added K loops. So that's a P1, a triangulation of the one gun to the K. So that is T must become, yes, there's a power of 2. Thank you. So T becomes 1. 2T P1. So there we are. Now we have completed, sorry, this was some P1. So now we have completed our functional equation. A triangulation of a one gun has either this structure, and this is the generating function of this first case, or it is a loop surrounding a loopless triangulation of the diagon in which every edge has been substituted by a watermelon. Okay. And so this is our second substitution equation. And now you can, so I can somehow rephrase this. So the series we knew well was the series P1. We had a cubic equation for it. Then we write that P1 is T, P1 squared plus T, and 2 of some T, and that is T is T over 1 minus 2 TP1. And as before, we eliminate T and P1 to get that a certain polynomial equation holds for N2 of T and T, from which you deduce that the same polynomial equation relates N2 of T and T. So that's one way of counting loopless triangulations. You could also apply Tutt's recursive approach, but then for higher connectivity, Tutt's recursive approach becomes very more tricky. And so in this case, so N2 is cubic. And again, you can determine completely coefficients, which are nice. You get an error. I should copy. Two to the n, 3n. N plus 1, 2n plus 1, loopless triangulations. With, so here it's n inner vertices. So it's triangulations of a diagonal. Is this the same numbers as we had before for non-separable maps? No, okay, so there's a factor 2 to the n here, whereas we had just 2 beforehand. So maybe I'll do quickly, or I'll sketch briefly the next step. So we had now 2 connected triangulations. We can go up to 3 connected and 4 connected, and there's even a paper on 5 connected triangulations. There cannot be 6 connected, so that's fine. So let's do as a final example the 3 connected triangulations. So for the 2 connected ones, it meant that you had to delete 1 vertex. Well, you had to delete 2 vertices to disconnect 1. And these ones you cannot disconnect by deleting 2 vertices. And again, we have a simple lemma, which I won't prove, which tells you how these triangulations are. So triangulation is 3 connected if and only if it has, so of course it must be 2 connected, so you can forget about loops, the loop, nor multiple edge. So you certainly don't want this kind of face, or here you have a pair of faces, which are certainly cubic, but you don't want to see that. So these are, so many people call this a triangulation. So these are those that you can draw with straight lines and real triangles, in a sense. So this is a real triangulation. So it's also, so they are no longer multigraphs, they are graphs, and they are also maximal planar graphs. That is with many edges. Okay, so we have to move one step higher in our construction. We started from those counted by P1 that had loops. We moved to those counted by N2 that had no loop, but could still have multiple edge. So this is certainly a loopless triangulation. And we want to move one step higher. So we start from N2, the non-separable triangulations of a digon. So certainly, well, it contains a double edge, since, yeah? So in general, it means that you cannot disconnect your graph or your map by erasing two vertices. So that's a matter of convention. Yeah, so I don't want the single edge here, I think. I mean, yes, you're right, yeah. So we'll see this through the construction. So you're true that at the moment in N2, I still have, I guess, I would have to check this. In N2, did I still have, yeah, so in N2, I still have the one edge map at the moment. So it has to be there. So when I do what I do here, so you're right, so there's still this case. So in my N2, so either it's reduced to an edge or there's more than one edge. And in this case, I have something like that. So here I have a triangular face. And then here I just drop this edge to get something with outer degree 3. So that's the first step. So that's a special case where I would get, I guess, just this. And then what I do, so I call this triangulation T. So I certainly still have, well, most likely I have double edges. And what I do in T, I will, I don't know, smash all multiple edges into a single edge. That is anything that looks like this with something inside. I contract into an edge. So in this way, I get a triangulation which, by construction, has no multiple edge. So 3 connected 1. And so I had started from N2. So I get, how should I call them, my triangulations? Well, let's call it T. So I get a real triangulation. Now the outer face is 3, or there's this the generate case here. And then to go backwards, I have to inflate every edge into a triangulation of a digon. So let me keep, that's an N2. Okay, so that's the simplest equation that obtained so far. Let me check with the initial. So there could be, but when I restore them, I'm not saying that these are two consecutive. There could be others here. I have shrinked everything. So it's a rugby ball that has become an edge, if you want. So this T is accounting for this edge. Yeah. Yeah, so I'm done. So you get something that by the same, this is a quartic as degree 4. It's algebraic. And you get again nice numbers. So the number, so for k internal vertices, you find that there are two 4k plus 1 k over 3k plus 2 k plus 1. So that's the number of 3 connected triangulations with k internal vertices. And there's a similar construction for the 4 connected ones and something more complicated for the 5 connected ones. So. Okay, and sorry for going over time.